Have you ever wondered why the reduced form of the electron carrier NADH is more energetic than the oxidized form NAD+? Well, if so, then you're a nerd. Yeah, that's right. You're a frickin' nerd. But it's okay. I might actually be a bigger nerd because today I'm going to try to explain to you why. NAD may be the most important coenzyme because it is necessary for cellular respiration, which is the most important metabolic pathway. This diagram represents glycolysis and aerobic cellular respiration. The goal of these combined processes is to convert glucose into ATP. ATP is really important because it's our primary source of cellular energy. Now let's see how NAD, our coenzyme in our electron carrier, is used during these processes. For every one molecule of glucose that undergoes glycolysis, we have 2 NAD+ being reduced into 2 NADH. Similarly, for pyruvate oxidation, we have 2 NAD+ reduced into 2 NADH. And for every turn of the citric acid cycle, we have 6 NAD+ and 2 FAD, which is another coenzyme and electron carrier, being reduced into their reduced forms. And notice for all of these processes, we have the lower energy oxidized form being reduced into a higher energy reduced form. By doing so, we're storing energy in these electron carrier compounds. And during the electron transport chain, we're actually doing the opposite, where we oxidize our higher energy reduced form into the lower energy oxidized form. By doing that, we're releasing that stored energy into the machinery of the electron transport chain. So we see our sums of reduced electron carriers are 10 NADH and 2 FADH2 being oxidized into their oxidized form. Throughout all of these processes, we generate approximately 32 to 38 ATP. Now this diagram might be intimidating at a first glance, but it's really what we were just talking about, but from another point of view. Notice that our x-axis is reaction progress and our y-axis is energy. And when I say energy, I mean the energy of our substrates, of our metabolites. Our initial substrate is glucose, and we can see that during the first few reactions of glycolysis, the energy of our glucose is rising. During reactions 1 and 3, we use ATP, and it's being dephosphorylated to make ADP. The phosphoanhydride bond of the ATP is broken, and the energy that it once held is transferred into our glucose metabolite, and its energy rises as a result. During reaction 6, we see that the energy of our glucose metabolite drops. That's because the energy stored in our glucose is transferred to NAD+, and that's in the form of a redox reaction. Our NAD+ is reduced into NADH. And that's the general trend for the rest of these reactions. We see during pyruvate oxidation in the citric acid cycle, the energy from our initial substrate, our glucose, is all being transferred via these exergonic reactions to reduce our electron carriers. And like I said before, the electron transport chain is then going to take all of our reduced electron carriers and it's going to oxidize them. And the energy from those oxidations is going to power the machinery of the electron transport chain, which eventually, as a result, is going to produce ATP. So now that we've talked about the function of NAD, let's take a look at its structure. NAD+ right here stands for nicotinamide adenine dinucleotide. So why is it a dinucleotide? Well, that's because we have 2 complete nucleotides in its structure. To be a nucleotide, one must have a nitrogenous base, a sugar component, and a phosphate group, and we have 2 of each. Adenine. Adenine is the name of this nitrogenous base, and you might be familiar with adenine if you know your A's and T's and C's and G's. Adenine is the A. Our other nitrogenous base is nicotinamide, which is, well, less common, but it's very important for the function of this compound. Nicotinamide is a pyridine ring with an amide functional group. The sugar component is ribose. You see we have 2 ribose. Now the most interesting part of this compound, in my opinion, is the way these 2 nucleotides are held together. We can see each has a phosphate group, and these phosphates are held together by what is called a phosphoanhydride bond. You can see I stretched out that bond a little bit for visibility. But this is different from the nucleic acids I'm most familiar with, DNA and RNA, because the DNA and RNA nucleotides are held together by phosphoester bonds. And a phosphoester is between a 3' hydroxyl and a 5' phosphate. So this bond is unique and interesting, and I'm tempted to call this whole thing a 5' diphosphate linkage, but I'm not sure if that's appropriate. So how does NAD+ differ from NADH? Well, all the chemistry involved in that redox reaction only concerns this nicotinamide nitrogenous base. Here I've redrawn nicotinamide in both an oxidized and reduced form. We see the differences in this positive formal charge on this nitrogen, whereas in NADH we have a lone pair, and in NAD+ we have one hydrogen attached to this carbon, which is sp2 hybridized, while in NADH we have a second hydrogen, and this carbon is now sp3 hybridized. So in order to do this reduction, this hydride ion must attack this carbon, forcing these pi electrons to move, forcing these pi electrons to move. The result is that new lone pair, this shifted pi bond, and this new hydrogen with the electrons it brought with it. But you're wondering, where did this hydride ion come from, and why did it choose to attack this carbon specifically? In order to understand why this carbon was attacked, we need to look at the resonance structures of NAD+. Here I've drawn out some major resonance contributors. We see that we have this positive charge show up in every form. This positive charge is delocalized across the pyridinium ring, but it shows up in several distinct cationic sites. It's at these sites where a nucleophile is likely to attack, as we saw with the hydride ion. Now, where does this hydride ion come from? Well, these redox reactions also include a substrate and an enzyme. Here's a general mechanism of how one of these reductions might take place. Our substrate represents our glucose metabolite. That's the glucose molecule that we kept manipulating and reacting to get all of our reduced electron carriers. This enzyme is a dehydrogenase enzyme, and their function is to bring our coenzyme and our substrate close together physically so this reaction can take place. They also can act as a base, as we'll see in this mechanism. Now, our basic enzyme, it really wants to take protons and donate electrons, and it's going to do just that. It's going to attack this hydrogen, and these electrons are going to move to this oxygen. Now we have a formal negative charge on our substrate, but we don't like that, so these electrons are going to keep on moving to form a double bond. However, this carbon can't have 5 bonds, so something's got to go, and that something is this hydride ion. This hydrogen is going to pack its electrons and say goodbye because it's attacking the NAD+, right at that cationic site we talked about earlier. These pi electrons move and these pi electrons move, and our result is a carbonyl on our substrate and our reduced NADH. Now, we've covered a lot of topics, but remember that the main question we're trying to answer is, why is NADH more energetic than NAD+? Well, reason one is resonance. Let's take a look back at these resonance structures. Here I've drawn out 5 resonance structures for NAD+. These are all good contributors to resonance. We have this pyridinium ring that's fully conjugated, and these pi electrons are free to dance and frolic and resonate wherever they want. Recall that having more resonance structures makes a compound more stable. In comparison, NADH is no longer fully conjugated. That's because we have this sp3 carbon right here, which limits the resonance of our pi electrons. If I tried to draw resonance structures, let's see what happens. I can move these right there, and I can push this bond to that carbon, and the result, well, if I keep going down this path, I'm going to get formal charges. Because these resonance structures have 2 formal charges, and this one has none, that makes this a major contributor to resonance, and these minor contributors. NADH resonates poorly, while NADH+ has great resonance. I can use this as a way to argue that NADH, since it has worse resonance, is actually less stable and more energetic, whereas NAD+, its resonance makes it more stable and less energetic. Stability and energetics are inversely proportional. For my second reason as to why NADH is higher energy, we must consider aromaticity. Let's recall our conditions for aromaticity. Our compound must be cyclic, which means it must have a ring structure. We have this pyridinium ring, so that is true. Our compound must be planar, which means it must be flat. Because all of these carbons are sp2 hybridized, the only possible geometry they could assume is trigonal planar, which is flat, so that is true. Our compound must be fully conjugated, and to be fully conjugated, you must have adjacent pi bonds, which we do have, so this is also fully conjugated. Finally, our compound must obey Huckel's rule, which says that the number of pi electrons is equal to 4n plus 2. Let's count our pi electrons. 1, 2, 3, 4, 5, 6. 6 is equal to 4n plus 2 if n is equal to 1. So yes, Huckel's rule is satisfied. Therefore, I can say that NAD plus is aromatic. If a compound is aromatic, it is very stable, which means it's low in energy. Let's look at NADH. Is it cyclic? Once again, yeah, it has that ring. Is it planar? Now this time we actually have an sp3 hybridized carbon, and this carbon isn't subjugated to trigonal planar geometry. It can actually pucker a little bit, and therefore I can't say that this is planar. Now, is it fully conjugated? Oh geez, well we got this sp3 carbon in the way and we don't have adjacent pi bonds anymore, so no, it's actually not fully conjugated. Does it obey Huckel's rule? Now let's see, we have 1, 2, 3, 4, 5, 6 pi electrons this time, so yeah, it does obey Huckel's rule. But because it's not planar and it's not fully conjugated, NADH is non-aromatic. It broke some of the rules and it is not aromatic. Being non-aromatic makes a compound less stable, and being less stable makes it higher energy. Therefore, I can use aromaticity as my second line of reasoning as to why NADH is higher in energy than NAD+. NADH, the reduced form of this electron carrier, is higher energy than NAD+, the oxidized form, because NADH has fewer, less stable resonance structures, and because NADH has a non-aromatic ring, whereas NAD+ has an aromatic ring. Thank you.